Okay, I thought I would post a video of me walking through one of the more complex problems that you're going to see on the test tomorrow so you can get some extra help. So this is a problem that you'll see that is combining two solutions, each containing two ions, and two of the four ions form a precipitate. So that's something that you want to identify first, is what the precipitate is that's insoluble, that would be coming out of solution. And you'd have your solubility rules to refer to figure that out. It's also good to draw a picture to get started and identify the four ions that you're dealing with. So if I had this example here, and you could pause this and try the problem and then check your answer. You could follow along, whatever you think is most helpful. So this is the picture that I drew for this question, where I gave two beakers and I wrote down underneath the beaker the molarity according to each one and the volume, and I drew out the picture of the ions in the solution. So it's important to understand that ionic compounds dissociate. So when we talk about sodium hydroxide, what we really have is individual sodium ions and hydroxide ions floating around. And so because there's one of each ion in the formula, the concentration according to each ion is the same as the original concentration that they give you for the substance. But as you can see in this beaker, because it's FeCl3, some of us get confused if it's a 2 because you think of that being diatomic. But we need to remember there's two ions there, iron and chloride, and this gives you the ratio of those ions in that formula. So when you put it in solution, you get 1 iron and 3 chlorides. And so the concentration according to the chloride is going to be 3 times, because that subscript, 3 times the original concentration of the substance. Okay, that's an important concept to make sure that you understand. And then I would go right to the net ionic equation. So if you try to write out the full reaction, I think that you'll get confused. Something good to do too is to write out a plan of where you're going, what you want to end up with. At the end, you want to make sure you have everything labeled. So off to the side, you could put in blank information that you'll fill in at the end. All of these examples have a precipitate, so you need to find the grams of precipitate that will form. And in this case, it's going to be iron hydroxide. We've seen this example multiple times in the labs, in worksheets, in prior tests. Hydroxides are insoluble except for your alkali metals and calcium, barium, strontium. So iron hydroxide is an orange solid that forms. You might remember that's when we use the centrifuge. So that's orange solid settled to the bottom. So then we might have leftover iron or hydroxide. It's possible we don't have either one of them if they react in the right ratio, but it's likely one of these is going to be our limiting reactant and one of them is our excess reactant. So we'll have to figure that out, and the best way to do that is use a table. And then these two ions are your spectator ions, so they're going to get diluted. They don't react, but they do change their concentration, because as the two beakers combine, the total volume increases, so the concentration is decreasing. Okay, so the next step would be to write the net ionic equation. So again, if the precipitate is iron hydroxide, and we're just writing net ionic, you would go ahead and write 1 iron reacting with 3 hydroxides to make 1 iron hydroxide. And again, this 3 is going to be important because it's going to tell us the ratio that these ions are going to react in. So for every iron, it needs 3 hydroxides. So after you write the net ionic equation, underneath it's good to write down the molarity according to each one. And again, make sure you go back to the formula and the example. And the iron was in the iron chloride, and it was 0.2 molar, and there was no subscript with the iron, so it's also 0.2 molar. If there was a 2 here, you would want to double it now to use it in the next table. And then the hydroxide only had 1 of it, so again we can use 0.1 molar. And then the milliliters of each one. Okay, so we should understand that if you take the molarity and multiply by the volume, you get a measurement of moles. And if you use milliliters, you'll get what's called millimoles. So what I'm beginning here now is a table called a BCA table. with what I have before the reaction occurs. So I have 70 millimoles of iron ions in one beaker, 45 millimoles of hydroxide ions in the other beaker, and obviously before I combine them I don't have any product yet. So again, what we need to do now is compare these amounts, because you're going to have one being limiting and one being excess, and this is where you use the coefficients. For every one iron you need 3 hydroxides. So this is something that you do in your head. You say, oh, I have 70 millimoles, and for every one iron I need 3 of these. So 70 times 3 is 210, which is a lot. You don't have that many, you only have 45, which means this is going to be an excess and this is going to be the limiting reactant. And again, you could go the other way. You could say for every 3 of these I need 1 of these. So if I have 45 of these, I will only need 15 of these. 1/3 of 45 is 15. And that helps get my change. So once I know the hydroxide is my limiting reactant and my iron is my excess, all 45 millimoles of the hydroxide is going to react, and you're not going to have anything left over. To get these numbers here, it's all based on the coefficients. So if I know all of this reacts, 45 of this reacts, I need 1/3 of 45, which is 15, reacting for the iron. For every one of these, you need 3 of these. So if 15 of these react, 3 times 15 is 45 of this reacts. Now to get that, for every one of these and 3 of these, you get 1 iron hydroxide. So again, if this is going down 15, this is going to go up 15. And so now you have what is remaining in millimoles of both the ions and your precipitate. So this is really important, and it's a really good, clear way to start the problem so that you have the pieces that you need. So now we're going to go and take the millimoles of the precipitate and figure out how many grams that is. So if I have 15 millimoles of the precipitate, we need to remember that 1,000 millimoles is equal to 1 mole. So there's 1,000 millimoles in a mole. And then this is the iron hydroxide. Okay, this is the precipitate that I'm trying to figure out. So now I'm going to use the molar mass. So the molar mass of iron hydroxide is 106.8. Okay, so this would give me my grams of precipitate. And I'm not going to worry about sig figs until I get to the very end and present my numbers. So I'll just keep some extra digits there. So I'm getting 1.602 grams of the iron hydroxide. Okay, so again, we use the table to figure out the millimoles of precipitate, and in other stoichiometry problems, what we would have done prior to this section, is taken the grams of one reactant, figure out how many grams of product that can make, and then separately take grams of the other reactant and figure out how many grams of product that it can make. But in this problem, you have 2 solutions, so you don't have gram measurements. So this is a simplified way to go about doing it. So we're sure we're getting this much because we considered the limiting reactant. Okay, so now I'm going to go and look at my excess reactant. So my excess was iron, so I'm going to figure out the concentration according to the iron. So it's real simple now because I know I have 55 millimoles in excess of that. So all we have to do is take 55 millimoles and divide by the new total volume. So again, if we took 450 milliliters of one solution with 350 milliliters of another solution and we combine them, we're going to assume volumes are additive because they're both aqueous solutions. So that adds up to 800 milliliters. So again, we talked about how millimoles divided by milliliters is the same ratio as moles per liter. So they both would give us molarity, and it just simplifies it for us. So this ends up giving me a molarity of 0.06875 molarity. Okay, and now it's off to my excess ions that are the spectator ions. So again, because the iron from one solution and the hydroxide from the other solution precipitate, my spectator ions are sodium and chloride. So to find out the concentration according to each of these, it's just a dilution problem. So to simplify this, we're going to take the molarity, original molarity of the sodium, which is 0.1 molar, and we're going to multiply by its initial volume, which is 450 milliliters. So again, molarity times milliliters gives us millimoles for the sodium, which doesn't change because it's not reacting, it's a spectator ion, but it is changing its volume, which means it's changing its concentration. So my new volume is 800 milliliters. So that becomes 0.05625 molarity. And then my other ion, I just want to be careful with the chloride. I want to point out that in the original formula, it's FeCl3. Okay, so when I say the original iron chloride is 0.2 molar, according to the chloride, initially it's 0.6. Okay, so if they give you this formula and there's a 3 in it, and they tell you it's 0.2 molar, for every one of these, you get 3 of these. So it's going to multiply by 3 and become 0.6. So we want to make sure that we're careful of the subscripts. So that's originally 0.6 molar, and that was in 350 milliliters. And then the new total volume is 800 milliliters. So that gives us a concentration of 0.2625 molarity. So we have everything we need. And again, I didn't worry about sig figs because now I'm going to write it on the bottom of my work or off to the side like I set this up. So if I go back to the original problem, I know everyone has concerns about sig figs, but we're just trying to keep it simple. So a lot of times molarity is just expressed in 2 sig figs. It's usually expressed maybe to the 100th place for different reasons, and if it's less than 1, that gives you 2 sig figs. And then this volume, it's not really specified. When they give you milliliters, they probably use the graduated cylinder, which is a pretty precise measurement of milliliters. So even though it might say 450, they might really have measured it to like 450 or 450.0. But again, we're limited by these 2 sig figs. So because the molarities have 2 sig figs, we're going to round everything to 2 sig figs in our final answer. So I'm going to go with 1.6 grams of the iron hydroxide. And then for the iron, which was the excess ion, I'm going to record that as 0.069 molarity. And then the hydroxide, if you remember, was the limiting reactant, so it has no ions left over. And then the sodium will be 0.056 molarity, and the chloride would be 0.26 molarity. And it's good to draw a picture to show your understanding. That may be something that I ask of you or give you a choice, or you'll see it in the future. So when our solution is, combined and done reacting, here's your precipitate, settles to the bottom. So there's 1.6 grams of it. That's the iron hydroxide. And then in solution, again, we don't have any hydroxide, so I'm not going to draw that. I have, if I look at kind of relative amounts of stuff there, kind of have a similar amount of iron and sodium, but have many more chlorides. So to kind of give, it doesn't have to be perfect. You're only drawing a few things. But maybe if this is like much more concentrated, just draw 1 iron and 1 sodium, and then a bunch of chlorines. And we don't have to show the water. We can say that the water is implied in it. And it might not be the right ratio, but it gives us an idea of, what ions are there, what's formed, and relative amounts. Okay? Thank you for paying attention. Good luck tomorrow.